Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, well, it's a pleasure to have Sardar Tasiran visiting us again. He'll be here for the entire week. He's been a frequent visitor to Microsoft Research. Currently, he's a professor at Koç University and in Istanbul, Turkey, and he's interested in both dynamic and static verification of concurrent programs. And today, he's going to tell us about his work on compositional verification of verifying transactional memory implementations. Okay.
Thank you, Shaz. Excuse me. This is more of a progress report on a project I started last summer. I believe so.
Okay.
Yes. And the project is on verifying software transactional memory implementations and a compositional method for doing so. There aren't that many repeat clients, so I guess I will repeat the part that I did last summer as well. So software transactional memory makes available a programming primitive to programmers. They get to mark code blocks atomic, and the STM implementation automatically guarantees that excuse me, that these blocks appear to be executed in an atomic, serialized, non-blocking way, and these atomic blocks are composable. This, of course, shifts the difficulty of concurrent programming to the STM implementer. They have to implement both optimal, high-performance code that is also correct. This code has to do conflict detection, rollback ordering, and other complicated things. But the hope is that transactional memory will be a widely adopted abstraction. Therefore, its correctness is as critical as other parts of your computing platform, such as your runtime, your compiler, your processor. Therefore, it is important to get implementations of transactional memory right. Real industrial scale implementations of transactional memory are on the order of tens of thousands of lines of code, and they interact in complicated ways with the rest of the runtime, the operating system, garbage collector, etc. Therefore, their verification is not a very straightforward, easy task for today's verification tools. And the goal of this project was to devise a modular, reusable method. If you're developing another STM implementation, the goal was for you to be able to use and reuse parts of this approach. And the goal was, again, to mechanically check the most error-prone parts, but do some of the proof manually still. And the key idea underlying the approach is that there are few approaches to building STMs at the algorithm level. At this level, STM implementations are well understood, and the key ideas in their correctness proofs, although they're not always written in the most formal way, they're well understood. And at this level, at the algorithm level, the model of an execution consists of large-grain atomic actions, such as field writes, field reads, transactions committing or rolling back. And for instance, if you look at the PLDI paper and the transactions paper on the Bartok STM, there is an intuitive correctness proof written at this level. So the idea of the work that got started last summer was to do this algorithm level proof once, using manual techniques mostly, and to translate the proof, to boil it down to a number of sufficient conditions which guarantee correctness. And then the idea is, in this case, these three properties would be checked off the STM implementation. And if the STM implementation satisfies these properties, then you're guaranteed that you get, for instance, serializability. And the good thing about the approach that we worked on last summer was that each of these sufficient conditions could be formulated as a sequential assertion check, which then we could hand off to Boogie and verify or find bugs in. Fortunately, the picture isn't as clean as this slide would lead you to believe, because the executions at the implementation level are more complicated than the ones in the previous slide with the large atomic actions. The complication comes from two factors. One, there are more variables that you need to be concerned with at the implementation level. There are variables that come from the STM implementation that implement, for instance, the transaction logs, the metadata associated with each object, etc. Also, at this more realistic modeling level, there are finer grain, smaller atomic actions. Therefore, a lot more interleavings to consider. An atomic action at this level is pretty much what the programming language gives you as an atomic action. One instruction in an STM function implementation. Therefore, reasoning at this level with these fine-grained actions and with this many variables is difficult. And a serializability proof or a correctness proof of whatever criterion you desire would be a lot more messy to write and check, and it would be a lot more error-prone. So the approach I'm going to talk to you about today is aimed at defining and proving a correspondence between these finer-grained interleaved executions at the implementation level and the algorithm level executions with bigger atomic blocks. And at the end of this, the algorithm level proof of correctness will carry over to implementation level executions, which is what you would want. And in pictures, what I'll try to go through today is to start with an implementation level execution to model it, and also to model an algorithm level execution satisfying these desired properties, and to go from here to there through a series of transformation steps. At this point, I don't expect you to read and understand all this text. Just pay attention to the four big gray arrows. Think of each of those as a way of transforming a detailed execution at this level to a more abstract execution at this level. Now, each of these gray arrows looks pictorially again like this. Imagine that each color is an action by a transaction, a different transaction. Black would be one transaction, red would be another, etc. And at the implementation level, they would be very interleaved, as you see in the bottom here. And each transformation step would do some abstraction, which would allow more actions to commute while leaving the execution equivalent to the original one. You would prove non-interference between certain actions, which would again allow you to realize that there are bigger atomic blocks. And at the end, you would get larger atomic blocks. And then you would repeat transformation of this sort to get even bigger atomic blocks. And the goal would be at the very top level to get transactions as your biggest atomic blocks. Now, what I'll talk about is the formalization of what I showed you in pictures. To talk about algorithm level and implementation level executions, I will define a very simple language, which is transaction heavy, but otherwise doesn't have a lot of the complicated other features of a programming language. And for this language, I will define two different semantics. One is at this level, the other one is at the implementation level. I'll formalize what correctness means on this language, and I'll show you a picture of the algorithm level proof, which is distilled to 3 required properties. The bulk of today's talk will be about relating executions at the implementation level and at the algorithm level. And I'll focus on what needs to be abstracted and what needs to be verified at the implementation level, and I'll conclude. So here is our transactional featherweight Java. And the things to pay attention to are there are statements, and there are statements that are allowed to be inside transactions, and there are statements that are not allowed to be inside transactions. In particular, you're not allowed to spawn another thread while you're inside the transaction. You can spawn as many threads as you want, but that can't be inside the transaction. And this statement that starts with onAcid and ends with commit is the transaction construct. Whatever is in between it executes, right? I didn't invent this, I wish I had. And each transaction is labeled. Other than that, you don't have much. You have assignment, you have method calls, you have sequential composition, and you have classes, fields, and methods. And you have parallel composition.
On as an implement, I should think as begin and end, right?
Begin, transaction, and transaction. But the inventor of transactional featherweight Java had picked those keywords, and I built on it and removed from it.
LSD.
Thank you for this. Thank you for the suggestion. Any other suggestions? Yes.
Does this mean you're not able to have sequential composition inside of a transaction? Where are we?
Doing the purple ones or the E's?
So,
Yeah.
no, it's allowed. You are allowed to do that. It's just transactional featherweight Java models sequential composition with actually a method call. The arguments to the method call are evaluated before the method itself. And in my effort at fixing that, I put it here, but not here. Thank you for the correction. So it shows that this work is not in its final form. It's work in progress, and this is a report on progress since last summer. So yes, you are allowed sequential composition, of course, inside transactions. Otherwise, they'd be trivial. Okay. So the purpose of this slide is to make you believe that there is actually formal semantics I associated with with this language, and this slide as well, and this slide as well. But of course, I'll tell you again in pictures what the algorithm.
Is that your work or somebody?
Yes.
Okay.
Right. So that will eventually be in the technical report. We're going to write about this. But pictorially or intuitively, at the high level, I model the program and STM composition in the following way. I don't model the inside of the STM implementation. The STM has the purpose of telling the program whether it's okay to commit a transaction, whether it's not okay to commit a transaction, and then also to undo some actions it's done as part of a transaction. The program, when it's about to begin a transaction, notifies the implementation, and when it's going to do a field write or field read, it notifies the STM implementation. When it wants to commit a transaction, it asks if it's okay to commit. If it's not, it has to roll back the transaction, and it does so, just one second, by the STM implementation telling it step by step to roll back the last action. I'm going to show pictures about each of these bullets.
Yeah, I have a question. I'm actually interested in seeing how this relates to your previous slides of the formal semantics. Do you describe the semantics of the OTFJ program as an automaton that can emit these commands and receive responses, or what's the connection here?
So let's look here, for instance. For instance, when you're doing a read field, first the STM implementation takes an action, and the STM state is transformed. So in the semantics, you have program state and STM state separately. It's a tuple that has both of those. And program state is a store for also a context for each transaction, and transactions can be nested, etc. So it's sort of a complicated tuple. But you have a program state and an STM state. And for each OTFJ statement, you describe how that translates to these state transitions.
So that's why there are two arrows there, because both of these states make an
Yes, and maybe I should immediately jump to the picture. So those two arrows, again, pictorially correspond to, first, the STM state making a transition, registering the open for read request. And then the program state makes a transition that corresponds to the read action. And also the program at this level, at this algorithm level, keeps its own log about what it did inside the transaction. For instance, if it did a read, it has its own log of. Why I chose to model this is a very sort of intricate matter, maybe that we can discuss afterwards. And how the STM implementation transforms its state in response to this request is left unspecified at this level. And all we're going to ask at the end of the STM at this level is to tell us when it's OK to commit, when it's not OK to commit. How it does so is its own business. Again, similarly with a field write, the program asks if the STM, if it's OK to write. Actually, it sends an open for write request. The STM tells it whether it's OK to write or not. If it is, then it writes, and then it adds to its log the old and the new value of the field that it's writing to.
But this log is in the STM string, right?
In reality, yes, of course. But at this level, we're pretending that the program keeps a record, pretty much a linked list of what it did inside the transaction. And when the STM says, no, you can't commit this transaction, it rolls back on its own. So at this level, my goal was to keep the STM state unspecified as much as possible so that the proof would boil down to these three requirements from the STM. But in reality, in Bartok, for instance, the STM has its log, and then it says each undo action is communicated to the program, and the STM tells the program, please undo this, please undo that, etc. Okay. And transaction commit is if the STM says it's OK to commit, it updates its state, then the program updates its state, and the logs, if it's a nested transaction, are appended to the parent transaction. Otherwise, if it's a top-level transaction, logs are discarded. The rollback is the trickiest. If the STM says it's not OK to commit this transaction because of conflict, then together the program and the STM take a sequence of transitions. Think of each of these as an undo last log entry order from the STM to the program. And at the end of this sequence of events, STM has finished its undoing of the transaction, and the program has reversed all the actions in the log, and it's as if the transaction can be retried from the beginning of the transaction again. Yes?
Why is the log on the program side? I would kind of expect it on the transaction.
So in reality, of course, like I said, it's on the STM side. But while defining the semantics here and while doing the serializability proof, in order to say here are the three requirements from the STM, but the logs are kept in the following manner in the program, it was more convenient to do so. Like I said, I realize that's not a very convincing answer right now, but the longer version is about 5 minutes long. All right. So, by the way, like I said, OTFJ builds on transactional featherweight Java, but TFJ is atomic at a much bigger level. Conflicts are not allowed to occur. The entire transaction executes in one go. So this is, by some authors' definitions, actually a low-level semantics already, because it allows conflicts, it allows rollbacks, and then it allows retries of transactions. And just to remind you, each of those slides, the story in each of those slides is considered atomic at this level. For instance, an open for read request followed by a field read, or an open for write followed by a field write, or the rollback of an entire transaction is considered one atomic sequence of events at this level. And to define correctness at this level, we first define equivalence of executions. Two executions are equivalent if they have the same set of threads, they end at the same program state, and when you project the actions to each thread is doing really the same sequence of actions, only the interleaving is different. And both of those have to be traces of this program, obviously. An alternative view at looking at equivalence is to say if you can obtain one execution from another by swapping independent actions that are adjacent, then you get an equivalent execution, where dependent means two accesses access the same variable and at least one is a write at this simple level. We also define something called equivalence modulo undos. It means look at two executions, remove all actions that rollback transactions do. Get rid of rollback transactions, pretend they didn't happen. If the leftover executions are equivalent in the way I defined above, then two executions are equivalent, modulo undos. Now, correctness is defined as serializability, and this has to do with a serial execution where if in the execution there are two actions by the same transaction, separated like this, and if in between them there is another action, then this red action has to either belong to Tx or a child of Tx, a transaction nested inside it. Right? It can't belong to an upper level or a transaction done by another thread. Conflict-free means no transaction needed to be rolled back. No transactions ever experienced a conflict. And a purely serial execution is an execution that's serial and conflict-free. Now, serializability is the requirement that each execution of this program STM combo is equivalent to a serial execution. And pure serializability is the requirement that each execution be equivalent modulo undos to a purely serial execution. Okay, so that's correctness. And with this definition of correctness and with this model at the algorithm level, these three conditions constitute a sufficient condition for pure serializability of an STM implementation. Between an open for write request and the corresponding commit or undo, no other transaction should write to the object that we're concerned with here. This is the exclusive writes property. The valid reads property says between the time that a transaction opened an object for read and it successfully committed the transaction, OBJ should not be modified by another transaction. Okay. Another transaction meaning another transaction not nested inside this one. And the correct undos property says the state of an object that is rolled back in a rollback transaction, the state should be right before the open for update, and the state right after the undo should be the same. So this is the property that you did the undos correctly. Okay. Then if your STM satisfies these three conditions altogether, then you're guaranteed pure serializability. But remember, this proof is at the algorithm level with the big, large atomic actions. Okay. Now, our goal is to now relate implementation and algorithm level executions so that these three conditions can now act as a sufficient condition for correctness at the implementation level. So let's start at the implementation level and do one transformation. But what is the implementation level semantics? The program actions that are reads and writes, etc., I don't need to refine those any further. They're the same in the algorithm level and at the implementation level. The actions of the STM, however, need to be broken down into smaller actions, sequences of smaller actions. So each action that I showed you in a picture that the STM did before is now a sequence of actions. And where does that sequence of actions come from? It's basically each line of code, each instruction in an implementation of an STM function. For instance, the open for update function. Think of each line as one of the epsilons on the previous slide. And of course, now the executions get to be interleaved at the epsilon level. For instance, an open for update by one transaction and validate read by another one get to be interleaved at this finer grain level. This is what complicates the picture. Okay, so here's one picture with the epsilons. Here's one picture again with the fine lower level actions. Okay, so when we take a closer look at each of these functions, we see that typically they have one atomic read or write of shared data, and the rest of the long code for the function consists of local variable accesses. Okay? This says to us, well, all of these actions, since they touch only thread local data, they can be commuted. They can be swapped with really any other action, except for this one. So commute everything to be adjacent to this atomic read. Except there's a glitch on this open for update function that does an atomic read and later an atomic compare and swap. Consider the following scenario where 2 copies of this are running concurrently. This one does a read, the other one does a compare and swap, as a result of which this compare and swap fails. Now, this cast and this cast do not commute. And this read and this cast do not commute because they all touch the same variable, and these are writes. Okay. So we were hoping that we would be able to compress the entire method into one atomic action, except it didn't work here. Then we play a modeling trick, and we say we allow reads to be a little looser. We replace reads with non-deterministic reads. So a non-deterministic read can either be nice and act like a regular read, or it can read an arbitrary value, in which case the cast associated with it in the future must fail. Right? Because it's going to fail, it doesn't really matter what it read. So remember, we're not changing the implementation, we're just changing our view, our model of it. We're adding to the set of behaviors. And if in this larger set of behaviors we're still able to prove serializability, then we're safe. And a non-deterministic read that leads to a failed cast commutes with all actions because it reads something arbitrary. It doesn't depend on any action that came before it. Okay. So now all of a sudden this non-deterministic read can commute across this cast to come over here, and the entire method is compressed. So now we did one gray arrow, one level of transformation where we were able to group all the actions that implemented the STM functions into adjacent atomic blocks. Yes?
So I want to think of that as the read thread local actions CAS that confirms the value read is still the same as one atomic action. That would also be a valid way of thinking about it.
Yes. Yes. If I understood you correctly, yes. Right. So we did one level of transformation. Yes?
To me, it seems that the critical point there is to prove that if it is interleaved, that the CAS actually will fail. Because the correctness of the implementation depends on the fact that the CAS is a reliable way to detect the interference of another.
Right. Right.
So somehow I didn't see how that went into your modeling trick.
So this CAS, I mean, we're not just abstracting the read into something more permissive. The CASs are also now aware of earlier reads that say you're bound to fail. It's as if there's an extra bit that says if someone does a CAS on what I read, he's bound to fail.
There is a known vulnerability of concurrent data types to CASs that succeed even though they should fail, which happens if you use pointer values as your CAS values. What can happen sometimes is that if a block gets freed and reallocated, so you have a new block which has the same pointer value as the old one. So you could get an execution where the CAS actually succeeds even though it should fail. It was like changed and then changed back to the original.
Right. In this case, the CAS is on what's called the STM word, which includes a version number inside, and that always gets incremented. Even though you may go back to the same object, same transaction, you'll have a bigger version number. So there are a lot of these implicit things we know about the program that I'm hiding under the rug here. I mean, when I said the rest are local accesses, that is a fact that I've confirmed by inspection. But right, yes.
So is it actually the case then? I mean, if I understand your trick correctly, is if you really implemented that first read as it just really does return an arbitrary value at runtime. That the algorithm indeed would be correct. It would just be terribly inefficient because very seldom would you get past the CAS.
Yes.
But everything is still correct. Is that the way to think about it?
Yes.
Kind of interesting because it says that says that really what the memory system should try to do is, when you ask for to read a value, it should just try to predict what value you would want in the future so you can make progress. But actually, it's allowed to return anything that it pleases.
Sure, there are caveats. I mean, if you're returning a pointer to some random corner of memory and then the code here is chasing that pointer and doing things, you don't want your code in between to crash, right? I mean, if you're reading an integer, it's fine. If you're reading a pointer to somewhere else, yes?
But from what Sebastian said, it seems like then there's more than just those 3 conditions for the STM to be correct. For instance, there is this. Oh, okay, but that's only in your model that you're forcing the cast to have this property that it's never going to rewind to a.
No, this is actually a property of the particular STM implementation I was looking at. It just never rewinds. I mean, of course, version numbers wrap around, but with that caveat, assuming unbounded integers, then it's a property of the code itself. It's not part of my modeling. It's not something I added in modeling. And this similar trick will come up in 2 more places in the rest of this presentation. Okay, so we started at the implementation level. We obtained what I called coarse atomic executions. We grouped some actions together. Now, one function in the STM implementation we can pretend is atomic. Now, this is where Boogie comes into the picture, and this is the part that had to do with the work last summer. Now, we're trying to prove something called the non-overlapping right spans property at the low level, which, when transformed to an algorithm level execution, will imply the exclusive rights property. Okay. So, the exclusive rights property, as it's stated, of course, you can't check that on the implementation level execution because there isn't an explicit commit action, for instance. There's a commit function that consists of many other actions. So think of the non-overlapping right spans property as the implementation level version of the exclusive rights property that's in the implementer's mind. And here, what we checked was an interval where tx1 opens an object for update and then later closes it. And another transaction, tx2, opens an object and closes it later, that these 2 intervals do not overlap at all. So this is the non-overlapping right spans property, and after enough transformations, it implies the exclusive rights property. And the way we phrased this condition and checked it with Boogie as a sequential check was as follows. We assumed that tx executed an open for update, and it succeeded. It has not yet closed the object. And then we wrote a property that says, at this point, tx is the exclusive owner of this object. Right. Then, if another transaction by another thread called txbad tries to do an open for update, it should fail, and it should not change this invariant. For instance. So we start with an open for update by the good transaction, the object. We say, okay, assume that this open for update succeeded. Tx good is the exclusive owner of object. Now assume that there is another transaction, and that other transaction tries to do an open for update. At the end of this, it should still be the case that Tx good is the exclusive owner. So this is sequential code, but it's mimicking and interleaving by 2 different threads by the fact that txbad and txgood are 2 different transactions. And if you verify this, if this assertion check passes in Boogie, then you've verified the non-overlapping right spans property. This is the easier one, the valid read spans property, which is going to eventually imply a valid reads property. That's the trickier one. Here, tx1 opens an object for read, and then later successfully validates that read before it commits a transaction. In this interval, there should not be an overlap with another transaction opening this object for update and later closing it. In other words, between the time I opened it for read and then I validated it, no other transaction should be in the process of updating that object. Right, so again, the sequential check formulated with Boogie goes as follows. I open the object for read. I'm going to later validate it. And in the meantime, I may also choose to open it for update. All of these are by the black good transaction TX. But in the meantime, interference may happen. Here, here, here. I'm going to show you our model of interference on another slide. But if at the end of all of these possible interferences, at the end, if interference occurred, if this is the same as the transaction having been invalidated, then that is what I want. In other words, if interference occurred, I want the transaction to be invalidated. If interference did not occur, then the transaction should have remained valid. Okay. And of course, the smarts is in interfere with here. Interfere with intuitively is modeling the effects of a pseudo regular expression where the bad other thread may close that word, may open and then later close that word, or may open it and leave it open. So the way we model that is in a while loop that iterates an arbitrary number of times. We pick a transaction non-deterministically. That's different from the good transaction that's going on. And this TX bad may open the object for update or may close the object. And this is an arbitrary number of iterations of this is what interference between my two actions is to me. Okay. Right, so
you have to do something to make that seems like it allows consecutive closes.
Yes, it does, but if right, and it also allows right. It allows closes without opens that happened in the past, or so you can think of this as more interference than could happen. But if I'm able to prove correctness with this, then I'm good.
If you had an STM implementation that assumed the correct pairing in order for the correctness of its implementation, but it could do arbitrary things, like still succeed if you mess. Never mind.
I see what you're saying. You're saying this is too pessimistic a model of interference, and this may give you scenarios that might not happen in your real STM implementation. And what I actually have implemented is closer to what you said, where opens and closes have to be matched, but that makes for a dirty slide. Think of this as, again, a sketch of what I had. For many reasons, including easier proof with Boogie, I did pair opens and closes if they exist. I'm trying to model the case where there's only a close or only an open without a matching other action. Okay. So, with this model for interfere with, this is the assertion we check with Boogie. Now, there's a while loop here. And loops create difficulty. I need a pre and post condition for this while loop. And Boogie has the abstract interpretation and loop invariant inference capability to actually infer what I need for this loop. But when I was trying to use it, it had a few bugs, so I actually wrote by hand a post condition for this loop, which basically said if someone interfered with me, then the version number actually has been incremented. Okay? And I verified that this pre-post condition pair was indeed correct by doing induction manually. I mean, the pre-post condition pair followed by one more iteration of the loop implies the same pre-post condition pair, the inductive step. So with that, I was assured that I had a correct pre and post condition for that loop, which I then fed to Boogie and checked this scenario. And I won't go into the details, but this approach found some interleavings that had been overlooked in the pseudocode. For instance, the pseudocode in the PLDI paper had an omitted case, a possible interleaving of events at this level, at the end of which the transaction should have been invalidated, but it wasn't. And I also asked Tim Harris and others of bugs that they had found in the past, but that were corrected now, of course. And they told me those, and when I modeled them, when I inserted them into the pseudocode, this approach was again able to find that the right thing was not being done in this case. So probably from an STM implementer's point of view, this is the most valuable part of what I did, where you have a mechanical way of checking possibly the most difficult part of this picture. The rest is just trying to put this into a formal context and trying to make it stand together as a big formal correctness proof. But much of that is manual, and this is the part that's automated. And you can think of this as checking whether the STM's way of ensuring those three sufficient conditions, using its own metadata logs, etc. Is that correct or not? Right. So checking that, I believe, was where the most value added was. But from a grand proof of correctness point of view, we have more work to do. Now we have coarse atomic execution. And when there's an, and I'm not really telling you how we got serial undos, but if you have the non-overlapping write spans and the valid read spans properties, you also get the fact that when some transaction is being undone, nobody else actually really interferes with it. Right? So a rollback is happening with no interference, really, as a consequence of these two properties. Let me show you the two more gray arrows. Okay. The first one has to do with inserting a commit annotation. If you remember, the OTFJ semantics said unacid as commit. So it was as if there was an atomic marker of where the transaction committed. Of course, at the implementation level, there's no nice clean, here's the commit point marker. I need to insert that by hand. And for a successfully validated and committed transaction, that is after the first successful validate read. A commit annotation is inserted there. And you can think of this as I'm putting some cosmetics on the implementation level to make it look like an algorithm level execution. So here's where the commit point is, which means it is my goal to commute all of the actions by TX next to, adjacent to this commit point, which with the validate non-overlapping read write spans and the valid read spans properties happens. It works. So because of those non-interference properties I checked, I know that none of these other things that got interleaved are actually dependent with these black guys, so they can all be commuted to where this black triangle is. The rollback transactions create some more difficulty with which we again fixed with non-deterministic reads. So here is a transaction being rolled back. The old values of everything that was written are written back. So object 1's field 1 is being reversed to what it was in the beginning of the transaction, etc., etc. And the problem happens. Okay, so this is the cosmetics. This is the taus in the slide that I'm inserting. Before each one of these, I insert a tau saying an STM implementation state transition occurred. You don't really need to pay too much attention to this, but this is interesting. I'm trying to commute all of the transactions actions over here, except if while I was undoing something I wrote, before I did the undo, if some other transaction read it. I mean, this read transaction is eventually going to fail, but I can't really commute these two, right? Because if I do, then this should have read something else. So here's a pesky read by a transaction that's going to eventually fail, but it's breaking my commuting plan. So what do? I again abstract this to a non-deterministic read, because in the future it's going to fail. The validate is going to fail. So when you change reads to non-deterministic reads that can read arbitrary values if they're part of a rollback transaction, then these non-deterministic reads get to commute with everything. And again, because I'm only adding to the set of possible behaviors, I'm not breaking any safety proofs. If I can prove serializability, pure serializability with these additional behaviors, then I'm okay. But now, this forces me to tweak the algorithm level semantics a little bit too. Because at the algorithm level also, this can happen. And at the algorithm level, I'm trying to group all the actions of a single transaction together. So at the algorithm level also, I need to allow failed reads that will eventually doom the transactions. Again, there too, I'm adding to the set of possible behaviors, possible bad behaviors. So probably liveness proofs would probably be very difficult to do with this, but if it's safety I'm after, then this is okay to do.
Did you think about whether it actually is safe for liveness? I mean, I could imagine that, if undoing one thread causes another read to fail. I mean, is it safe? Or let me say this: is it live? I mean, is there?
No, it's not. Clearly, you could have bad non-deterministic reads happening all the time, and no execution ever gets to commit.
Approximation, right? So
yes,
any property, any universal property you prove on the abstraction is going to hold on the concrete.
Right. Safety properties are fine,
including liveness properties, if you're able to prove it on the abstraction.
Yes. I'm saying it will be difficult to prove with this over approximation. It will be difficult to prove any liveness properties.
That is a problem for any kind of property. You might create an abstraction on which you're not able to prove a property.
Right. Yes.
I'm confused. In the previous introduction of non-deterministic reads, the value read was input to a later CAS that deterministically read something and confirmed the non-deterministic read. I don't see where that would be for this sort of non-deterministic read.
So in this non-deterministic read, the state of the STM is modified. The STM state that is taking care of this other transaction. So if I do a non-deterministic read that reads an arbitrary value, I notify the STM of this fact. And later, when this read is validated, even though it may not have been touched in the meantime, it will fail. In some way, it's analogous to...
Is there a loop around this? Where it fails, does it get retried or something?
Yes. So in the semantics, any transaction that fails has to start from the beginning and be retried.
So you're just making transactions fail more often?
Yes.
Okay. Does that answer your question?
But
I think it's probably my fault for being confused, but
no,
you're going forward. You're doing this non-deterministic read. Do you do all reads non-deterministically?
Yes. So all of the good cases are there because in all of the original behaviors are there because in each case the read can act the way it acted in the original implementation. But sometimes it can read random garbage, but in which case that fact is communicated to the STM. The state is changed. And although there may not be any actual interference, the STM fails that transaction.
These particular reads are guaranteed to be bad reads. Because
Yes, in this particular scenario, they're guaranteed to be bad. I'm doing it in this particular case to allow me to commute it over here because I want to collect all the good black guys together. And this really is an irrelevant read that will fail. It's immaterial that the read got interleaved at that point. Another way to look at this is, I guess, never mind. I mean, this really could have happened over there, but in which case it would not have been invalidated. So Never mind. In this particular scenario, this transaction was going to fail anyway. I'm not artificially making it fail.
But I mean, I think your point is that you don't have an execution in front of you when you decide to abstract that action. You have program text in front of you. Mm-hmm. And then you say, okay, I'm going to abstract this action. Mm-hmm. And that action, once you decide to abstract it, that abstract action could have executed either in this kind of scenario or in the scenario where it should not have failed, right? But then you're adding more behaviors.
Yes.
But that's okay.
Right. So, I mean, in that case, more transactions will get rolled back and retried unnecessarily. Okay. So, after the cosmetic additions to the implementation level executions, after you merge sequences of taus into a single tau, sequences of chains of STM internal state transitions into one long single update of the STM state, and after you insert these marker actions, etc., what you get, and there's a simple proof of this, what you get is actually an algorithm level execution according to the high level semantics. And if you proved these properties here at the top level, they imply the exclusive writes, valid reads, and the correct undoes properties. So with all this manual transformation, abstraction, etc., I've proved to you that every implementation level execution is equivalent to an execution that's an algorithm level execution that has the EW, VR, and CU properties. Therefore, my model of the Bartok STM, the executions it can generate, are all purely serializable. Okay. So, I have difficulty holding all parts of this argument in my head a lot of the time. So
actually, can you go back to the previous slide?
This one?
I just want to test my understanding. I'll
Sure.
say a few sentences.
Sure.
So you're saying that you verified every implementation level execution satisfies pure serializability. I think what you actually ended up verifying is that a wildly crazy abstraction of the actual implementation satisfies not just those executions, but a lot more executions satisfied.
Pure serializability.
Because of all this extra non-determinism you added,
Yes.
you were very careful that you did not lose any of the behaviors.
Yes.
Okay?
Yes.
You just added all those extra behaviors to make the proof easy, which you're allowed to do.
So that's a very important point, right? Why did I do all of this? Because the proof at this level, with all the interleavings that can happen, an inductive proof is very messy, very error-prone. I mean, it's difficult to talk about the program state and something. It's difficult to write something you can say about it at this level. But after you swap enough things, you get an execution on which you can do an inductive proof, and you can rest somewhat easier that inductive proof it works. But now, the cost is you don't get these very clean properties that you can check at this level. You have to transform them to something you can check along the way, right? Because you don't have these clean commit points, for instance, at this level. So you have to check these somewhere along the way, something that's a sufficient condition for these conditions along the way.
It doesn't seem like a drawback. It seems like that's reality.
Yes. Yes, I guess
have these spans of time during which bad things shouldn't happen.
Right.
If that's all true, then you get these nice properties.
Yes, I guess you need to translate the concept of periods up here to a concept of periods down here, and it's inescapable. You're right.
I mean, I have another question. Why do you need those properties? Why can't you just think of one piece of state and you are just trying to construct transactions at the top, right? Why do you need, I don't understand why you need those properties.
At this level, you mean?
Yeah.
Um,
So your algorithm is also a program, right? Whatever story you're doing down there, you can keep doing that story until you get all the way to atomic actions.
But at that very top level, saying I can group everything that belongs to a transaction together, that is a manual inductive proof. And that proof needs these properties.
Why does it have to be manual?
well, even if you mechanize it, you need these properties that say, well, since the last transaction that committed, the following kinds of undesirable things did not happen. Right? I mean, the way I did that proof is by induction on the number of committed or rolled back transactions. So to say something about what happened since last time a transaction committed or rolled back, and now this one, to argue about what actions may have transpired in between, you need these properties that say, oh, that some bad stuff did not happen.
Is it fair to say that like the core automatic piece is the part that you did with Boogie? Mm-hmm. The whole rest really is a way of completing the picture, basically making that automatic piece fit with everything.
Yes. Yes. But, I mean, executions at this level and at this level are not the same. And somehow they need to be related to each other. So it's not just writing Greek letters, it's really making sure that reasoning at this level carries over to the implementation level. But in terms of catching bugs, yes, I mean, this is the part where...
One thing that you use to make this correspondence is that you have these names for operations that stay sort of the same all the way through. Is that correct?
The program's actions are exactly the same.
Okay.
Right? The STM actions are first broken down, interleaved in many different ways. Then through modeling, proofs, etc., they're grouped together to sequences of taus. You group them into one big action by the STM implementation. So what you get in the end looks like an algorithm level execution. Because down here you verified these, up at this level you get these. And if you have those, then you have pure serializability.
I guess it was helped. The fact that the basic operations at the very bottom, you can still recognize what they're doing in terms of...
Yes. Yes.
I'm not sure if that's true for all kinds of data types or libraries.
No. I mean, it did help that when I was writing the algorithm level semantics, I actually knew what was going on down here. So that if I grouped enough actions together, I would get, for instance, a commit or a rollback or something like that. Right, so the top level proof very much has the logic of a lazy-invalidate right-in-place STM in it. The semantics I provided for it has that characteristic in it. And I mean that's part of the reason the log is on the program side and not on the STM side. Right, the program knows that it's a lazy-invalidate right-in-place.
Is the proof at the algorithm level not a serializability proof? The proof of correctness in that part?
Yes, it's a pure serializability proof. Remember, if you throw away rollback transactions, what you get should be still an execution of the program, no conflicts, and serializable. I mean, serial.
I see.
I mean, you're confused.
Is the complication why you had to do it manually that the program, there was a universal quantifier over the input program?
Right. So the top level correctness proof has universal quantification over threads, transactions, all possible sequences of accesses you could have in a transaction, over objects, etc. And you have to say something like, since the last commit point or since the last rollback, what happened in terms of program state, in terms of shared central store, is as if only I executed and no one else did. Right? And to say that, you need to say all my reads were valid. No one else wrote in the meantime. And when I wrote, nobody else had the object for write in the meantime. So, I mean, the execution actually really is purely serialized. Just to argue that it is so, you need to have the assurance that between open for update and validate, nobody else changed the state you care about.
Then all you needed to do that proof was that the lower level thing, the implementation level thing, could be abstracted into a sequence of actions where each action has a particular semantics.
Yes.
At that level, you're using the semantics of those actions.
Yes.
So then, why do you need So in answers to Sebastian's question, you said that there's some name matching is important, right? No name matching is important. You just need the semantics of these actions.
No, I mean, again, this is happening because I didn't tell the entire story of how the STM works. So before you commit, where's that? Before you commit a transaction, you first validate all of your reads. If they were all valid, then you close all of your objects. The commit point of this transaction is after the first validated read. Right? So I mean, so yes, you are going to commute things together, but to what point? To where the commit action happened. Right? I mean, if you try to commute these over here, it won't work. So right, I mean, you're grouping things into bigger chunks, but next to what action are you grouping everything together? And you need to pick that carefully. I mean, I didn't come up with this commit point. If you read a paper about a lazy-invalidate write-in-place STM, they say, yes, this is the commit point after the first successful validate read. Remember, in the higher level, there's one giant commit action that says, get rid of the logs, go on. Okay. Yes?
Can I try one more time to understand the slide you just went past with the introduction of the second use of non-deterministic?
This one, sure.
So I understand the first one, I think. It's kind of like value speculation in hardware. I'm going to read a value speculatively, I'm going to compute some local things, and then I'm going to either throw it away or use them based on what the value actually is now, with a deterministic read. In the program text there, you can say this original read, the first read before the CAS, is going to be a non-deterministic read. I don't understand here, when you're reading the value of the field as separate from the value of the TMW, of the version number of the object containing the field. Are you determining statically or dynamically that it's non-deterministic? And what do you confirm it with? Are you relying on some connection between the version number and the value later? Those seem, if so, those seem very different. Because in the first case, you're confirming the actual value of the location you read, and here you're reading something else to confirm the value of something you read.
So, let me tell you my mental picture of it, and maybe that will help, maybe it won't. So, if I'm a field read, when I'm about to occur, I make a decision. I'm going to be regular or I'm going to be crazy. If I decide to go crazy, I let the STM know. Eventually, when you try to validate me, regardless of what else may have happened in between, just invalidate.
So how did you let the STM know in that case?
I think that the tricky part is that he actually can see the future, because he is given the entire execution when he starts his proof and has to show.
Right. I'm not changing the implementation. I'm changing the semantics I assign to it. Therefore, I can make this read tell the STM that I went crazy, therefore invalidate this transaction in the future. So transactions, when they do a bad non-deterministic read, go into crazy mode, at the end of which they have to fail and roll back.
That is almost suggesting that you're changing the implementation's logic, right? You're not just abstracting individual action. What do you mean you notified the STM that you went crazy? The original STM doesn't know anything about crazy. You're adding behavior.
Right, so think of Andy read as different field read, where when I'm notifying the STM, there's another extra bit which I set if I went crazy.
Okay.
So there's one bit. I non-deterministically decide whether it's 0 or 1. If it's 0, I act normally. The STM acts normally.
Later the STM reads that bit?
In validate read, it says if this bit is set, regardless of everything else, I just fail this transaction.
How do you know that you created a valid abstraction of the legal execution? Because now your implementation, see, you added an auxiliary variable, right? If the auxiliary variable is just sort of doing something, right, and you're not influencing the implementation of the behavior, then you know by construction that you have an abstraction. But now how do you know you have an abstraction?
Right, so when that bit is 0, that gives me all the original behaviors.
Okay.
So remember, this bit is part of the STM implementation. Therefore, in terms of program variables, adding this has not changed anything. Now, all the original program behaviors are there because they all could happen with this bit remaining at 0.
Because there was a non-deterministic choice here,
Yes.
you could have said 0.
Yes.
Okay.
In that case, read is the regular read, validate read is the regular validate read.
Okay.
If it's 1, they act a little bit differently,
Okay.
but this is just all just additional behavior.
Does that make sense?
Okay. I guess so.
So, but this bit was something you added explicitly for the purpose of doing proof, right?
Yes. But it's, in my mind, it's the same as the read cas story.
No, that's fine.
So formally, it's sort of an instrument in semantics that abstracts the underlying concrete semantics.
Yes. Yes. Exactly. Right. So.
I think the issue is that if you tried, this wouldn't work very well if you tried to do an inductive proof, because you wouldn't know in advance whether the read is going to fail later on or not, right?
What do you mean by inductive proof?
So with inductive proof, I mean you're trying to show that for all executions there exists an equivalent atomic execution, but instead of looking at the whole execution, you're trying to prove this based on one step at a time.
Well, you'd have to do it, I guess, for all executions where these bits play out a particular way, maybe.
No, the serializability proof is for all executions with the bit set to 0 and to 1. But remember, if it's set to 1, that transaction is rolled back. So all I care about is that rollback executed correctly. If it succeeded, it only succeeds when the bit is 0.
Yes, I guess what I'm trying to say is if you think of your actual implementation, and then you think of your more abstract behavior where you choose to be crazy or not. If you try to show that your actual implementation refines your specification, if you try this using a simulation at the time where it's time to decide whether you're crazy or not, you don't actually know whether you're going to be crazy
That's
or
true.
not.
So at the time of proof of serializability, it's as if I can see forward and backward through the entire execution.
So put another way, the fact, that checking that you did not remove any implementation behavior, that's in your head, right? You didn't actually mechanize it. You didn't ask Boogie to check that.
No. I mean, there's the only part that's mechanized is the part checked with Boogie. All of the rest is on paper and pencil.
So that part, I think, if you try to mechanize it, you might run into problems. It might not be able to prove that you have more behavior, strictly more behavior.
In terms of program variables.
You have to show somehow that in each step you are adding more behaviors, right? The thing is that if you just take an action of the program, right, and you make it more non-deterministic, it's a very local check that you added more behavior, right? But in your case, the argument for why you added more behavior and did not remove any behavior is more global. It requires all this reasoning that here I'm setting this bit and later on some access to that bit is doing something, whatever.
Let me just say, I believe that proof is easier than you're thinking probably. Think of the original state space and the original behaviors, and these other crazy state spaces. Every so often you can jump to the crazy state space, but you come back, and when you come back, you know that you come back to the same state.
Well, supposing there's a transition back from the crazy state space to the lower state space, right? Which set bit back to 0, right? Then the whole thing is screwed, right? So somebody has to check that you never come back from the crazy state space to the real state space.
Right, so I have to argue to you that when I come back to from the crazy state space back to the real state space, that I come back to the state I left in. But that's easy because undos are being done serially. Anyway, right, so I don't know how to argue objectively that whether something's easy or not.
I don't think there's any argument. Ultimately, it has to be done by the computer.
Yes, as I argue more and more of this, I realize that more of the proof needs to be done mechanically and checked. Right.
How hard was the bottom part where you take the actual implementation and you coarsen it up by showing, that it is atomic? I think you mentioned one non-deterministic read trick, which is, sort of a non-trivial.
That's it. That's it.
That's it.
Yeah.
So the rest was, how automatic could the rest have been again?
It's automatic in the sense that you see the text of the methods that constitute the STM implementation, and you see that each of them have either a single shared variable access, or they have two of the format that I showed you, in which case the argument I explained. So I mean, that
seems very automatable. Correct?
Yes, yes. Right. So to summarize, to formalize correctness, I defined a language that had transactions in it, but not much more. Defined pure serializability. So I hadn't, right? So first, remember this serializability notion has nested transactions inside it also, and rollback transactions because it says it's pure. When you throw away rollback transactions, what you get is still an original program trace. I wrote an inductive correctness proof at the high level, which distilled the requirements from the STM to these three properties. I related implementation and algorithm level traces. For this, I needed to play some modeling tricks. And this way of relating the two executions allowed each of these properties to be checked mechanically on some model of the implementation level execution. And I want to mechanize more of the proof, look at other kinds of STMs and see if a modular and this transformation kind of approach is applicable to them. And what I verified is still a model of the implementation. It's not the C# or C++ code. And again, it's at the same level of granularity as the real implementation, but there is really no formal relationship between my model and the actual implementation. So how to make that more formal is something I need to work on. I guess this is really, really future work to look at weak memory models. Thank you.
One thing that might be interesting, the Bartok the Bartok STM you modeled has the property that if two transactions don't conflict, then they don't, abstractly, then they don't conflict in their implementation. Mm-hmm. Some other STM implementations don't have that property, like TL2, in which there's a global version number that writing transactions increment. So two transactions that don't have any intersection between the read and write sets might actually conflict at the implementation level. So that might be an issue with your commuting-based proof style.
True. The witness trace at the algorithm level can't be obtained by simply commuting things. You need to throw away some stuff, I guess.
So sometimes in that case, even if transactions are independent, at the higher level, there might still be conflicts at the lower level, and it might actually ask the transaction to retry, abort.
Well, no, but it's atomic increments of a shared variable, and the correctness doesn't care which, in that case, which order they happen in, but the values obtained would be different.
For the variable, for the shared variable.
Yeah.
But you can use the same trick there also, right? You can completely abstract that shared variable.
Yeah, maybe it's a new style of abstraction.
Yeah. I mean, in general, I think one thing that is going on in Serdar's proof is that abstraction is a weapon for generating more commuting actions.
Right.
And I mean, this non-deterministic read is just one kind of abstraction. You can imagine lots of different kinds of abstractions. And in fact, Typhoon is a student of Serdar. He's working on a tool that actually tries to mechanize proofs like this with iterated commuting arguments and abstraction arguments.
And actually, originally I had abstracted the CAS to non-deterministically fail, even when it would have succeeded. But this non-deterministic read seemed more widely applicable, so I thought one kind of abstraction is better. And if I understand correctly what you were saying, I do what I call a throwing away of rollback transactions, but I do that only at the top level. In what you described, I guess some of that throwing away has to happen in the intermediate steps. where these failed transactions have to be removed from the trace.
I'm not sure.
Okay. Right.
I think the version number is an interesting example because Charles is right. If you abstract the actual number and say it's just a unique identifier, then you commute. But the problem then is that in some cases it's actually a number that is ordered because you care about the order in which that's. So you have to, when you do this abstraction, you have to know when is it just an identifier and when is it actually an order.
So I think the thing is that as you keep abstracting from the lowermost level, right? You discharge different steps of the proof at different levels. So at the point when the actual value of that number is important, at that point you can't do that abstraction. But once you have taken care of that part, now your algorithm is a little bit more abstract. At that point, now you can just sort of toss it away and you get more commutativity. So it's basically the different arguments are going to happen at different parts of the abstraction.
Yep.
And I like to think, I'm not sure I can claim it, but that this is at least partly the picture in the designer's or implementer's head. This is probably how he convinced or she convinced herself that they implemented transactions correctly. Otherwise, I can't imagine how they thought about all possible interleavings at that really fine level and thought, well, regardless, I have something serializable.
One more comment. You abstracted away issues of wrapping of version numbers.
Yes.
And the schemes for dealing with that, which is a pretty important practical concern, are pretty damn subtle. If you're interested in places where there might actually be bugs, that might be some place to look at what Tim did for Bartok in this area and see if that could be fit into the proof. Might be really interesting.
Right. And other things I abstracted away, like I said, when I say only the red boxed lines touch shared data and the others don't, it's not really immediately obvious. For instance, if other code decided to behave badly and chase pointers, they could access local data in other transactions, erase logs, etc. So either by inspection or through static analysis, I need to ensure that the part of the code I didn't model isn't doing these evil things and erasing other transactions, logs, etc.
You'll have to model the counter as a 32-bit value rather than as a logical integer, right? But maybe you can just model that one as a 32-bit integer and leave the others as logical integers.
Right.
Sometimes it's a good idea that you can just model it as a 2-bit integer.
Yeah, exactly. You just want to know that when it wraps over, things don't go bad. So.
Oh, I see.
Because
You can just model
why
like a
wait
bunch of
for
Boolean
why wait
variables.
for 2 to the
Okay.
32nd to do that? Just do it much sooner.
Okay, thank you.
All right, let's hang the speaker.